بسم الله الرحمن الرحيم. بنرحب فيكم في هذه المحاضرة عن الأوبتمايزيشن. اليوم بدنا ناخذ بعض الباك جراوند المهم لنا في دراستنا. So today is a background lecture. أول شغلة رح ناخذها في الباك جراوند هذا إن نراجع إحنا وياكم what is called the Taylor series expansion. Taylor series expansion. Okay. أي function, a function can be expanded about some nominal point x star. So f of x is our function, and we need to use the Taylor series expansion to represent it. So it is equal to f of x star plus d f of x by dx applied at x equals x star times x minus x star plus 1/2 d2 by dx squared of f of x applied at x equals x star times x minus x star, the whole thing squared, plus we keep continue until infinity actually, plus 1/n factorial d to the power n dx n f of x at x equals x star times x minus x star to the power n plus up to infinity. So this is the Taylor series expansion. F of x, or f at x, the nominal point, plus the derivative, the first derivative, with delta of x, which is x minus x star. The derivative is applied at the nominal point. 1/2, which is 1/2 factorial, d2, the second derivative of f of x applied at x star times delta of x squared, and we keep continue up to infinity. This is actually can be applied to any continuous function. Okay. Let me take an example and see how we can implement this. If we let f of x is equal to cosine x. So the Taylor series expansion of f of x about the point x star equals 0 is f of x is equal to cosine of x, which is equal to cosine of 0 minus the derivative of the cosine is minus sine, so it's minus sine of 0 times x minus 0 plus 1/2 d2 of x. d2 of x sine minus sine x, the derivative of it is minus cosine, so this is minus 1/2 cosine of 0 x minus 0 squared plus 1/6 sine of 0 times x minus 0 cube, and we continue, and we end up with cosine of 0 is 1, sine of 0 is 0, so this one is 0, sine of 0 is 0, so this one will be minus 1/2 x squared plus 1 over 24 x to the power 4, and we end up like this. So this is what we call the Taylor series expansion for the cosine signal. I will just do another example. Maybe you can relate it to calculus. The example is also very simple. If we let f of x is equal to e to the x, so f of x is equal e to the x, then the Taylor series expansion of f of x about the point x star equals 0 is f of x, which is equal e to the x, which is equal e to the 0 plus the derivative of f of x is e to the 0 times x minus 0 plus the derivative of e to the x, second derivative, is also e to the 0, 1/2, sorry, e to the 0, x minus 0 squared plus 1/3 factorial e to the 0, x minus 0 cube, and we continue. So this one will be 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1 over n factorial x to the n. So this is e to the x, and this is, I think you know this from calculus. So this is the Taylor series expansion of e to the x also. Okay. Okay. Sometimes if we are very close to in the vicinity of the point, the fixed point that we have, the point that we are looking for the Taylor series expansion about it, if you are in the vicinity of that point, so delta x is very small, you can find an approximation, and you can say that around, let me put it in another way, if x is very close to x star, this means that delta x is very small. We can approximate f of x using truncated version, truncation of the Taylor series expansion. So if delta x is very small, the fourth order, the third order, the second order, and all of those will be very small values, so you can truncate the Taylor series expansion and have a good approximation for f of x using the Taylor series expansion. Okay, so we can say that our fourth order approximation for cosine of x using Taylor series expansion is f of x is equal to 1 minus 1/2 x squared plus 1 over 24 x to the power 4. Okay. All right. I'm going to expand this Fourier series expansion in multi-dimensional. So this is only for one-dimensional or one-dimensional signals. So we'll do what we call the vector case. Vector case for Fourier series. We will say that, okay, if we have variables or vector, f of x is equal to f of x1, x2, up to x sub n. So you have an n number of variables. How can we do the Taylor series expansion for those? Then also f of x is equal to f of x star, where x star now is a vector of a point in the nth dimensional space, and this is equals to f of x star plus partial x1 f of x evaluated at x equals x star. Now you have a partial derivative with respect to the first element multiplied by x1 minus x1 star plus partial x2 for f of x evaluated at x equals x star multiplied by x2 minus x2 star, and we have to go for all the n's, first derivative of all x of n's. So this will give us the partial x of n of f of x at x equals x star multiplied by x sub n minus x sub n star. Then we go to the second derivative, and we will do this for the second derivative, 1 over 2 partial x 1 squared of f of x evaluated at x equals x star multiplied by x1 minus x1 star squared plus 1/2 partial x1 partial x2 f of x evaluated at x equals x star as a vector multiplied by x1 minus x1 star times x2 minus x2 star, and we keep until infinity. Notice that here we did all the partial derivatives, first order partial derivatives for all elements, then the second partial derivative with x1, then the next one with x1 and x2, x1 and x3, x1 and x4, and we keep doing all those derivatives in this manner. Okay? It's more convenient to write this in a matrix form, which will be much easier to understand. So I'm gonna write it in a matrix form. So it is more convenient. It's more convenient to write it in a matrix form. So f of x as a vector is equal to f of x star as a vector plus the gradient transpose of f of x evaluated at x equals x star multiplied by x minus x star plus 1/2 times x minus x star transpose times the Hessian of f of x at x equals x star times x minus x star. Those are vectors. So those are vectors. The dash underneath means that this is a vector of x. It contains all the elements of x as a column vector. Okay, and then plus third element, which is 1/3 factorial, whatever. So we are much more concerned. Our concern is with the first derivative, second derivative, and once we have x minus, which are the deltas, sorry, yeah, okay, this is transpose with this one is the square values. Okay, notice that you don't have a square here. This one multiplied by this one multiplied by this one give us the square that we have here. Okay. What are the symbols that we have? Those inverted deltas. Where this one here, the del of f of x, and we call it here the gradient. The gradient of f of x. Okay, is the gradient of f of x. And it is defined as the gradient of f of x. Actually, it's a vector, which is equal to the partial derivative of f of x, partial x1, partial derivative of f of x, partial x2, until partial f of x, partial x sub n. So this is the gradient, or the definition of the gradient, while the del squared operator is called the Hessian, and it's a matrix. So this is the gradient, and the del squared of f of x is the Hessian matrix, and is defined by is equal to the matrix second derivative of f of x partial x1 squared, second derivative of f of x partial x1 partial x2, until second derivative of f of x partial x1 partial xn. And we go to the next item, second derivative of f of x partial x2 partial x1, second derivative of f of x partial x2 squared partial x partial x2 partial xn, and we go down systematically until we reach partial 2f of x partial xn partial x1 partial 2f of x partial xn partial partial x2. And the last one is partial second derivative of f of x partial xn squared. Okay, this is the Hessian matrix. So we can, this is a more convenient way to represent the Fourier transform using the multiple variables. If you have a multiple variables and f of x is a vector, actually x, our x vector is equal to x1, x2, up to x sub n. So this is our vector, the actual vector x of n, or the x, sorry. Okay, enough from the Fourier series expansion, and let's move to, and we'll see this in later examples. We will demonstrate that, and how to find the Hessian and how to find the gradients. So we'll use this or those concepts in the examples later on. Okay, let's define something else called the directional derivatives. Okay, let's define the following. The ith element of the gradient, which is partial f of x partial xi, is the first derivative of f of x along the xi axis. So this is the first statement. The second statement, the ith element of the diagonal of the Hessian matrix, which is partial 2 f of x partial xi squared, is the second derivative of f of x along the xi axis. Okay, so taking this into consideration, we can find something called define something called the directional derivative. So we need to find the derivative in the direction of a p vector this is called the directional derivative. And can be computed as P transpose the gradient of f of x. So the inner product, it's the inner product of b in the direction of f of x. So you do the inner product between the vector p with the direction, with the gradient, and you end up with the derivative in the direction of p. So that p, the amount of b is not an issue, so we will divide by the norm of p, so that we will take just only a unit vector in the direction of p. So p over p is equal up, which is a unit vector in the direction of p. So we need to find the derivative in the direction of p. We do the inner product between p and the gradient. Okay? To find the second derivative, along p can be computed as p transpose the Hessian of f of x times p divided by the norm squared of p. So this is the second derivative in the direction of p computed with the Hessian matrix. Okay? P transpose the Hessian matrix times p, and this is the answer. Let me just take an example and demonstrate how can we find directional derivatives. Okay, let's take the following example. If we let f of x is equal to x1 squared plus 2 x2 squared. So this is it has a minimum at 0. It's like a parabolic volume centered at 0 and goes in the dimension, in the third dimension, in the z dimension. And we want to know the derivative of the function at the point x star equals to 0.5 and 0.5 transpose in the direction p equals to 2 minus 1. Okay. Solution. First of all, let's find the gradient of f of x. Let's just find it, the gradient of f of x, which is equal to partial f of x, partial x1, partial f of x, partial x2. So this is equals to, so you have f of x. What is the partial derivative of this one with respect to x1? This one will be considered constant, so this is 2x1. x2, it's 4x2. Okay? What will be the gradient evaluated at of 0.5 and 0.5. So 0.5 and 0.5, this is x1, and this one here is x2. And this one is a vector, actually. This is in the direction of x1, and this one in the direction of x2. So what will be this one? 0.5, so this is 1, and 0.5, so this is 2. So this is our gradient at this point here. Okay. Now, we need to find the direction or directional derivative. So it's the inner product of the gradient at this point with this vector here. So the derivative or the derivative in the direction of P, which is equal to 2 and minus 1, is P transpose the gradient of f of x of times P, which is equal to 2 minus 1 multiplied by 1 and 2 divided by the magnitude of P, which is 2 and minus 1, and this is equals to 2 minus 2 divided by the square root of 5. The magnitude of 2 minus 1, second order norm, is the square root of 2 squared plus minus 1 squared. This is equal to the square root of 5. So this is equals to 0. So it seems that once you get a 0, it means that the gradient at this point and the vector, they are normal to each other. They are perpendicular on each other. If we just draw a rough diagram showing an x1 and x2 plane, and we will draw the contours, the contour plot of f of x, contour plot, or sometimes we call them level curves. We have like parabolic level curves or contour plots. They are centered at 0, and they expand more in the x-axis, so they look like this. So they are like ellipses, and so on. So these are the values. If we take this to be our 0.5 and 0.5, and this one is our P vector, which is at 2 and minus 1. So this one 0.5, let's call this to be 1, and this one here to be 2 and minus 1. So the slope here and the vector, so this is in the direction, this is the direction of P, and the direction of the gradient is in this direction. It's 2 and 1 actually, so it's supposed to be 2 and 1. It's supposed to be 90 degrees. P should be perpendicular to the f of x at x equals to 0.5 and 0.5 transpose. So this one here is perpendicular to this one here. So f of x is perpendicular at the tangential of P. Okay? Okay, we will stop here today. Tomorrow or the next lecture, we will start talking about different types or definition of minimas, and we will define minimas and use the Hessian and the gradient to calculate or manipulate minimas and work with them. Thank you very much for being with me today, and see you next lecture.